Hello everyone. Myself Mr. S.M. Ghanwat working as Assistant Professor in Mechanical Department at Sharad Institute of Technology College of Engineering Yadrao Ichalkaranji. In this session we are going to discuss part 3 of equilibrium diagrams. In part 3 of equilibrium diagrams we are going to discuss one component or unary phase diagrams. Also, we are going to discuss binary phase diagrams. Now, we are going to discuss one component or unary phase diagrams. Much of the information about the control of the phase structure of a particular system is conveniently and concisely displayed in what is called a phase diagram, also often termed an equilibrium diagram. Three externally controllable parameters that affect phase structure are temperature, pressure, and composition, and phase diagrams are constructed when various combinations of these parameters are plotted against one another. Perhaps the simplest and easiest type of phase diagram to understand is that for a one component system in which composition is held constant. That is, the phase diagram is for a pure substance. This means that pressure and temperature are the variables. This one component phase diagram or unary phase diagram, sometimes also called a pressure temperature diagram or PT diagram, is represented as a two-dimensional plot of pressure versus temperature. Most often, the pressure axis is scaled logarithmically. We illustrate this type of phase diagram and demonstrate its interpretation using an example of H2O, which is shown in figure. Regions for three different phases, solid, liquid, and vapor, are delineated on the plot. Each of these each of these phases exist under equilibrium conditions or the temperature-pressure ranges of its corresponding area. The three curves shown on the plot, labeled AO, BO, and CO, are phase boundaries at any point on one of these curves. The two phases on either side of the curve are in equilibrium or coexist with one another. Equilibrium between solid and vapor phases is along curve AO. Likewise, for solid-liquid boundary, curve BO, and liquid-vapor boundary, curve CO. Upon crossing a boundary, as temperature and/or pressure is altered, one phase transforms into another. For example, at 1 atmospheric pressure, during heating, the solid phase transforms to the liquid phase, that is, melting occurs at the point labeled 2 on the figure, that is, the intersection of the dashed horizontal line with the solid liquid phase boundary. This point corresponds to a temperature of 0 degree centigrade. The reverse transformation, that is, liquid to solid or solidification, takes place at the same point upon cooling. Similarly, at the intersection of the dashed line with the liquid vapor phase boundary, point number 3 in figure, at 100 degree Celsius, the liquid transforms into the vapor phase or vaporizes upon heating. Condensation occurs for cooling. Finally, solid ice sublimes or vaporizes upon crossing the curve labeled AO. As may also be noted from figure, all three of these phase boundary curves intersect at a common point. which is labeled O. For this H2O system at a temperature of 273.16 K and a pressure of 6.04 into 10 raised to minus 3 atmospheric. This means that at this point only all of the solid, liquid and vapor phases are simultaneously in equilibrium with one another. Appropriately, this and any other point on the pressure temperature phase diagram where where three phases are in equilibrium is called as triple point. Sometimes it is also termed an invariant point in inasmuch as its position is distinct or fixed by definite value of pressure and temperature. Any deviation from this point by a change of temperature and or pressure will cause at least one of the phases to disappear. Pressure temperature phase diagrams for number of substances have been determined experimentally, which also have solid, liquid, and vapor phase regions. In those instances when multiple solid phases, that is, allotropes, exist, there appears a region on the diagram for each solid phase and also other triple point. This is the information about one component or unary phase diagram. Once again, we are going to discuss this one component or unary phase diagram. In this phase diagram, in this system, there is no composition change. Thus, only variables are temperature and pressure. Thus, in a region of single phase, two variables, temperature and pressure, can be varied independently. If two phases coexist, then according to phase rule, either temperature or pressure can be varied independently, but not both. At triple points, three phases can coexist at a particular set of temperature and pressure. At these points, neither temperature nor the pressure can be changed without disturbing the equilibrium. That is, one of the phase may disappear, and this is shown in figure also. We are going to illustrate this with the example of water or H2O. The figure is going to demonstrate you the interpretation using the example of H2O, which is shown in figure. Regions for three different phases, solid, liquid and vapor, are delineated on the plot. Each of these phases exist under equilibrium conditions over the temperature pressure ranges of its corresponding area. The three curves shown on the plot labeled AO, BO and CO are phase boundaries at any point on one of these curves. The two phases on either side of the curve are in equilibrium or coexist with one another. Equilibrium between solid and vapor phases is along curve AO. Likewise, for the solid-liquid boundary, curve BO and the liquid-vapor boundary curve CO. Upon crossing a boundary, as temperature and/or pressure is altered, one phase transforms into another. For example, at 1 atmospheric pressure, during heating, the solid phase transforms to liquid phase, that is, melting occurs. At the point labeled 2 on figure, the intersection of the dashed horizontal line with the solid-liquid phase boundary, this point corresponds to a temperature of 0°. The reverse transformation, liquid to solid or solidification, takes place at the same point upon cooling. Similarly, at the intersection of the dashed line with the liquid-vapor phase boundary, point 3 shown in figure, at 100°, the liquid transforms into the vapor phase or vaporizes upon heating. Condensation occurs for cooling. Finally, solid ice sublimes or vaporizes upon crossing the curve labeled AO. As may also be noted from figure that All three of the phase boundary curves intersect at a common point, which is labeled O. For this H2O system at a temperature of 273.16 Kelvin and a pressure of 6.04 into 10 raised to minus 3 atmospheric. This means that at this point only, all of the solid, liquid and vapor phases are simultaneously in equilibrium with one another. Appropriately, this and any other point on the pressure temperature phase diagram where three phases are in equilibrium is called a triple point. Sometimes it is also termed as an invariant point, as its position is distinct or fixed by definite value of pressure and temperature. Any deviation from this point by a change of temperature and or pressure will cause at least one of the phase to disappear. Pressure temperature phase diagram for a number of substances have been determined experimentally, which also have solid, liquid and vapor phase regions. In those instances when multiple solid phases exist, there appears a region on the diagram for each solid phase and also other triple points. This is all about the one component or unary equilibrium diagram. Now we are going to discuss the binary phase diagrams. Another type of extremely common phase diagram is one in which temperature and composition are variable parameters and pressure is held constant, normally 1 atmospheric. There are several different varieties. In the present discussion, we will concern ourselves with binary alloys, those that contain two components. If more than two components are present, phase diagram become extremely complicated and difficult to represent. An explanation of the principles governing and the interpretation of phase diagrams can be demonstrated using binary alloys, even though most alloys contain more than two components. Binary phase diagrams are maps that represent the relationship between temperature and the composition and quantities of phases at equilibrium, which influence the microstructure of an alloy. Many microstructures develop from phase transformation, the changes that occur when the temperature is altered, typically upon cooling. This may involve the transition from one phase to another, or the appearance or disappear appearance of a phase. Binary phase diagrams are helpful in predicting phase transformation and resulting microstructures, which may have equilibrium or non-equilibrium character. Now we are going to move further with our next discussion regarding binary isomorphous system. Possibly the easiest type of binary phase diagram to understand and interpret is the type that is characterized by the copper-nickel system. Temperature is plotted along the ordinate and the abscissa represents the composition of the alloy in weight percent bottom and the atom percent of nickel on the top. The composition ranges from 0 weight percentage on the far left horizontal extreme to 100% weight on the right. Three different phase regions or fields appear on the diagram, and alpha field, a liquid field and two-phase alpha plus liquid field. Each region is defined by the phase or phases that exist over the range of temperatures and compositions delineated by the phase boundary lines. The liquid L is a homogeneous liquid solution composed of both copper and nickel. The alpha phase is a substitutional solid solution consisting of both copper and nickel atoms and has a FCC crystal structure. At temperature below about 1080 degree, copper and nickel are mutually soluble in each other in the solid state for all compositions. This complete solubility is explained by the fact that Both copper and nickel have the same crystal structure (FCC), nearly identical atomic radii and electronegativities, and similar valences. As already discussed, the copper and nickel system is termed isomorphous because of this complete liquid and solid solubility of two components. Some comments are in order regarding nomenclature. First, for metallic alloys, solid solutions are commonly designated by lowercase Greek letters, that is alpha, beta, gamma, etc. With regards to phase boundaries, the line separating the L and alpha plus L phase fields is termed as liquidus line, as indicated in figure. The liquid phase is present at all temperatures and compositions above this line. The solidus line is located between alpha and alpha plus L regions, below which only the solid alpha phase exists. For figure, the solidus and liquidus lines intersect at the two composition extremes. These corresponds to the melting temperature of the pure components. For example, the melting temperatures of pure copper and nickel are 1085 degree and 1453 degree respectively. Heating pure copper corresponds to moving vertically up the left hand temperature axis. Copper remains solid until its melting temperature is reached. The solid to liquid transformation takes place at the melting temperature, and no further heating is possible until this transformation has been completed. For any composition other than pure components, this melting phenomena occurs over the range of temperatures between the solidus and liquidus lines. Both solid alpha and liquid phases are in equilibrium within this temperature range. For example, upon heating of an alloy of composition 50% weight% nickel 50%, melting begins at approximately 1280 degree. The amount of liquid phase continuously increases with temperature until about 1320 degree, at which point the alloy is completely liquid. This is all about the binary isomorphous system. Now we will move further with our discussion of interpretation of phase diagrams. For a binary system of known composition and temperature at equilibrium, at least three kinds of informations are available: the phases that are present, the compositions of these phases, the percentage of fractions of these phases. The procedures for making these determinations will be demonstrated using copper and nickel system. Now we will summarize the binary phase diagrams. These diagrams constitutes two components, example two metals or a metal and a compound or two compounds, etc. In most engineering applications, as mentioned before, condensed phase rule is applicable. It is assumed that the same is applicable for all binary phase diagrams. Thus, the presentation of binary diagram becomes less complicated. Thus, binary diagrams are usually drawn showing variations in temperature and composition only. It is also to be noted that all binary systems consist only one liquid phase, that is a component is completely soluble in other component when both are in liquid state. Hence, binary systems are classified according to their solid solubility. If both components are completely soluble in each other, the system is called as isomorphous system. Extent solid solubility for a system of two metallic components can be predicted based on Hume rotary conditions summarized in the following. Crystal structure of each element of solid solution must be the same. Size of the each atoms, each two elements must not differ by more than 50%. Elements should not form compound with each other, that is, there should be no appreciable difference in the electronegativities of two elements. Elements should have the same valence. All the Hume rotary rules are not always applicable for all pairs of elements which show completely solid solubility. In system other than isomorphous system, that is, in case of limited solid solubility, there exist solid-state miscibility gaps. Number of invariant reactions can take place. Intermediate phases may exist over a range of compositions. These intermediate phases may undergo polymorphic transformation and some may melt at a fixed temperature. A solid solution based on a pure component and extending to certain finite compositions into a binary phase diagram is called as terminal solid solution, and the line representing the solubility limit of terminal solid solution with respect to two-phase solid region is called as Solvus line. This is all about the binary diagrams. Now we are going to see the reference part. For this session, the reference is William D. Callister Jr., David G. Rethwich, Material Science and Engineering, an Introduction. For further reading, you can refer this particular reference book for Introduction to Material Science and Engineering. Thank you.